we are about to start the last session of this conference. I think all talks which we have seen consumed a lot of effort of their authors. But I think this one, which we are going to hear now, is a particularly difficult one because it is a summary talk of all the things which we heard here. So it's my great pleasure to present Marumi Kado from the Max Planck Institute and ask him to show us what he considered the best out of this conference. Marumi?
Thank you very much, Danek. So this is a beautiful picture of the poster of the conference, and it was really a breathtaking overview of high-energy physics. And I want to really stress that there's been really a wealth of new results. And I'll try to give you an overview and highlight some of them. Of course, unfortunately, I will have to skip many of them, and I sincerely apologize for those superb results that I will not be able to present here. And I start with the quote of the closing remarks of yesterday's panel by Soshi Asai, saying that we should enjoy the physics, and that's what we'll try to do in this last talk. I prepared just a brief slide which summarizes the general framework and all the motivations of why we're doing all this. But because we really want to go to the results, I'm just going to skip it and leave there just for reference. I'm going to start with a brief discussion of the main facilities, the main colliders that were presented by Sergey on Tuesday, yesterday. And first, with the LHC, which is really refining its results on a clean, well-calibrated data set. All the results you've seen so far, most of them were on the Run2 dataset, and it's a very clean and well-calibrated dataset, and this has allowed us to do fantastic physics so far. Of course, since now 2022, we started data taking also in the Run3, and we've got already about 120 inverse femtobarns of data, which is the equivalent of the Run2 dataset. So if we look at the performance of the machine, and this plot has been shown by many of the speakers, you can see the data taking as a function of time for each of the years, and you can see that gradually, each of the years, you see that the data taking is more and more effective and performant. One thing that's very important, and the message that was given by Sergey, is that in 2024, we had very high availability of operation and full mastery of considerable inherent operational risk. What this actually means is that there are many issues, but all of the issues are always very, very effectively and fast and rapidly resolved. So we're standing really halfway through the LHC operation schedule, and truly in a year, and just slightly more than a year, on the horizon, we have the next long shutdown, the third long shutdown, which is the preparation for the high luminosity phase of the LHC, which is the critical time for the LHC. And so far, we expect for the high luminosity phase to have 10 times more data. But truly, in terms of results, since most of the results we've seen so far were with Run2 data, the results that are expected for LHC are going to be expected with 20 times more data. Sergey also made a fantastic review of all the accelerator, and maybe one of the important highlights that he pointed out is the sudden beam losses in SuperKEK B, which are, of course, of great concern and have to be addressed and understood. And this is what SuperKEK B is focusing on currently, and currently also Bell 2 is currently running without its vertex detector because of these issues. He reviewed also many of the accelerator facilities, and I will refer you to his slides for this. So let me jump immediately on the physics, and I will start with the Higgs sector. And in the Higgs sector, there are three main pillars of Higgs physics. And I will start with the first one, which is this decay of the Higgs boson to two vector bosons. And as Matthew was saying, this decay and this measurement is of utmost importance because it is the best measured coupling that we have at the LHC. And because it's the best measured coupling that we have at the LHC, it's the one that's constraining the most the compositeness of the Higgs boson. And you can see, and that was presented by Nicolas, we have already reached a 6% level precision on the coupling of the Higgs to the W and the Z boson. And we foresee at HLHC to reach the level of 1.5 to 1.7%. But of course, this was with analysis done a long time ago, and we surely would be able to do better, and I will be discussing this in a moment. And for the future facilities, we really want to go down to the level of the per mil. And this is important because if we look at the Higgs boson currently, its composite net scale is at the same level as the pi-n is for QCD. Another very important message that Matthew gave us was that precision in physics is key, but it's key also through the precision predictions that we have at the LHC. And this is not only higher order predictions, but it's also PDFs and alpha S. And I'll be discussing this also in this talk. Also, Sakura gave us a very nice overview of what formal theory is doing. And formal theory is doing not only doing very formal aspects that don't have an immediate impact on our physics, it's also doing a very precise calculation, in particular, the multi-loop level calculation through amplitudes and fantastic mathematics that is being done there. And I can show you also a beautiful new result that was prepared for this conference by CMS. This is a differential cross-section in the Higgs to ZZ decay, and also you can see here the progression of the cross-section as a function of center of mass energy. Nicolas also gave us the picture of the measurements of the coupling of the Higgs boson to fermions, and you can see here the precisions that have been achieved at the LHC so far, and the ones that we expect to have at HLHC and then at future colliders. One important new result that was also presented was from Atlas, and here you can see is the production of the Higgs boson in association with the pair top quarks, and you have a beautiful event display here of this very complex signature that was discussed by Nicolas. And you see that this result, which is actually the best single measurement of the Higgs coupling to tops done so far in Atlas, has a significance of almost 5 sigma by itself. And this is quite a challenge, because of course there's a lot of statistics, because the Higgs boson is decaying to BB bar, so it's the main decay channel. And however, it has a huge amount of background, which is very complex to understand, and it was quite an achievement to control this. But also, as Matthew was saying, it was very important to have very precise predictions of the signal to be able to extract the signal coupling in this channel. In particular, he shows the TTH production at next to leading order that was computed just quite recently. Another very important aspect that has been discussed in many talks, these are maybe the plots that have been shown the most in all of the conference, and this is the evolution of the flavor tagging performance as a function of time and as a function of new AI algorithms, machine learning algorithms that have percolated the field, in particular going to graph neural networks, and I will discuss also a few more by CMS. And you can see that the progression has been really astonishing. And one question that was asked also during the plenary session was whether there's room for improvement. Is this a Moore law? So of course, there are physical limitations to how far you can go in tagging BJets. However, this GN2 here, for example, has not been used in the analysis so far, and there's also room for improvement since many of the aspects that can discriminate flavors of jets have not been used so far in there, for example, soft leptons. There was a beautiful talk by Javier on AI in high-energy physics, and you can see that there's a huge array of machine learning opportunities, which is beyond classification, regression. AI is moving towards simulation, unfolding, anomaly detection, particle flow algorithms, and so on and so forth. One thing that is extremely important, I think that one take-home message that I thought was very important in what Javier said, is that new ideas also have to be concerned by robustness and interpretability. This is extremely important, of course, in everything we do. Another beautiful measurement that has been shown is the Yukawa coupling to charm at the LHC, and this was done by 2 experiments. One new result presented for this conference was the Higgs boson coupling to the charm quarks. So of course, at this point, we only have limits, and the limits, if you look at the achieved limits on, for instance, the coupling to the charm quark here, they don't look very impressive. If you look at the same analysis in CMS, where they have similar results, but they have pushed and looked at the prospective at the HLHC, you see that with this type of sensitivity that we currently have, we can reach a precision on capacity of 40% per experiment. What this means is that with the improvements of the flavor targeting algorithms, we should be able to get to the level of first evidence, at least with the 2 experiments. And this is a very important breakthrough, which was enabled by AI algorithms. Another important aspect of the couplings of the Higgs bosons is the Higgs bosons which are probing particles to the loops. And here we have several couplings that have been measured, effective couplings to the photons, the gluon, but also the Z-gamma. So there's a huge progress also on that front, measuring couplings to vector bosons through loops. And you see here the current measurements and what we will be reaching in the future. Here the numbers that have been estimated were estimated with very old analysis. It's going to be very important for the upcoming European strategy to have an update of these numbers. And also, one very interesting coupling that is often not put forward, maybe I would say sufficiently, is that we've measured actually one specific coupling of the Higgs boson, which is the coupling of the Higgs boson of 2 Higgs boson and 2 vector boson. And what's interesting in this analysis is that we have observed this coupling in the sense that it cannot be 0, but we have not observed di-Higgs production. And this is because if this coupling was to be 0, the level of signal would be too high, and this is excluded. And this is a very, very nice result that shows that this coupling cannot be 0 in the standard model. And finally, one of the most important goals of the next phase of the LHC is the trilinear coupling or the self-coupling of the Higgs boson. And here I want to quote what Matthew said. Despite the fact that in vanilla SUSY and vanilla composite model, it is difficult to have large deviations in the trilinear coupling. So the general idea is that it's impossible to have large deviation in the trilinear coupling while having small deviation in the Z boson couplings. However, he and Georg in parallel session have shown that it's actually fairly easy and possible to have large deviation in trilinear coupling while small deviations are kept for the Z coupling. This is a very, very important result and show how important it is to have this coupling, even at the level that is the projection of the HLHC. And in particular, if we look closely at the sensitivity that's going to be reached at the HLHC, there are these 2 new results. One new result with a combination of the HH analysis in Atlas. And here we really just focus on our ability to observe a signal HH in Atlas and CMS. And you can see that so far, both experiments have reached an exclusion sensitivity of 2.5. And in both cases, the observed limit is actually larger than the expected limit. And what this implies is that there are small excesses in both experiments. In fact, in Atlas, there's a 0.4 sigma excess, and in CMS, there's a 1 sigma excess. If you look at the sensitivity in terms of observation of this process, both experiments have 1 sigma. So if you take the 2 experiments, 3 times the luminosity at run 3, this immediately leads to a 2.5 sigma sensitivity with the 2 experiments. What this means is that with improvements in the flavor tagging, in the analysis, at run 3 and also in the trigger that have been carried out in both experiments, at run 3, we should be able to reach close to a first evidence level of significance with the 2 experiments in the HH. And this is absolutely an outstanding goal of the 2 experiments. Okay, I leave this here for reference. Now, we also seen, with the LHC going towards precision, very nice measurements of scan square theta W, which were presented by Maurizio and Yasmin, both by CMS and LHCb. The CMS number is quite impressive. It gets to 31 in 10 to the minus 5. And this is the most precise measurement of sine square theta W done at the LHC. And if you look closely, you'll see that it's comparable to the measurements done both at LEP with the forward-backward symmetry in the B and at SLD. And these are the 2 best measurements done so far. So there's a huge range of improvement that we can still do in these measurements, which gives us a really bright future in precision at the LHC. Here you see the beautiful measurement done by LHCb, of course, with less luminosity, but fantastic systematic uncertainty as well. Another very important process that was a measurement that was discussed also this morning by Kirill Melnikov is the measurement of alpha S. And I was very pleased by what he said. In particular, what are the conditions to have a very competitive measurement of alpha S? And these are to be proportional to the strong complete constant, a measurement that can be predicted theoretically without percent precision at next to leading order, at better than percent precision next to leading order and higher orders. It should be independent of bad uncertainties like PDFs and so on and so forth. And what's interesting is that he deemed that the inclusive Z production, the differential Z production in transverse momentum actually seems to fit the entire bill of what he said as conditions. And this is very important because through the measurement of the Sudankov peak of the transverse momentum of the Z, we can make a measurement of alpha S, and this is actually the best measurement so far, the best single measurement of alpha S so far. And it is free of many of the difficult systematic uncertainties. Of course, this is still under discussion, but you can see that the precision now is below the percent level, and it's at the A/mil level. Kirill also mentioned the W mass measurement and how in Atlas the way it's measured is depending on the ratio of the W to Z transverse momentum. This is a key observable. And of course, this is going to be relying on the simulation. And it's extremely interesting because he pointed out that if you look carefully at QCD and electroweak correction, you see that there are actually shifts that can be of the order of up to 20 MeV. And this is interesting, but however interesting this might be, you can see that the difference between the Atlas and the CDF, for instance, just take two of them, is still extremely significant at the level of 4 sigma. In fact, the correction that he was pointing out is bringing the Atlas measuring down, so it's going to increase the significance. So why is this important? Is because we have to keep in mind that we cannot look at a comparison of the measurement with predictions and the standard model as long as we have a very strong tension between the measurements. So this is a puzzle, but primarily it's an experimental puzzle that has to be resolved by the experiments. Okay, and then finally, I just wanted to flash 3 beautiful measurements of dye boson production at run 3 that were shown and discussed this morning by Philippe Sommer. Let me go now to the quark sector and start with the top quark entanglement that was discussed this morning by Dida. And what's interesting is that top quarks, when they are produced at ADC, they are not polarized. However, there's a strong spin correlation. And you can see this when you look at production at threshold, where actually the production of a pair of top quarks are in a Bell state. So when you have a spin in one direction, you necessarily is going to have the spin in the opposite direction for the anti-top. And this is what we call a Bell state, and it's maximally entangled. So this was already measured, for instance, by Atlas, and the effect was seen at threshold. It's the place where it's most easy to actually see and witness entanglement of a pair of top quarks. But CMS came with a fantastic analysis showing that it could not only look at the threshold, but also at high mass, meaning what the two tops are boosted, one respect to the other. What this means is that this gives a much larger fraction of space-like events, meaning they cannot be connected by light, one to the other. And this is also extremely interesting because it brings us in the realm of being able to test the Bell inequality violation in top decays, in top production, sorry. And then we continue with puzzles, and this is long-standing puzzles in VEB and VCS, and there are new measures made by Bell2 and Babar of VCB that show in the exclusive channels B to DL nu and B to D star L nu, and these measurements are actually showing that the measurements of VCB, yes, VCB, sorry, is moving exactly. I got this wrong. Yeah, okay. Yes, measurement of VCB is actually now going in the exact right direction. I don't know what I have this wrong, I think. In the right direction and release the tension that there was between the inclusive and the exclusive measurement of VUB and VCB together. Also, we've discussed a lot lepton universality, And as you know, the RK star was cancelled from LHCb in the end of 2022. But still, there was a 2 to 3 standard deviation in the angular distribution and the absolute branching fraction of B to K star mu mu in the angular distribution. And you see here a very nice measurement done by CMS of the angular distribution variable P'5, and this is an observable, which is interesting because it's essentially free from any form factor uncertainty. And LHCb has made an analysis, comprehensive analysis of local and non-local amplitudes to this decay, and shows that here now you should be comparing this blue curve here to the measurement, which is the brown curve here, instead of the yellow prediction of the standard model. And you see that the tension has also been released in this angular distribution, and the tension now is down to 2.1 sigma. Also, still testing the lepton flavor in universality, you have a very nice analysis that was done by LHCb, presented by Yasmin, of these same parameters, an angular distribution done in the electron channel, and also perhaps one of the most interesting channels in terms of searches for new physics, which would be flavor dependent. And you see here, for instance, the decay of B to K star tau tau, and this we have a first result done by Bell2, and you see that the limit here has been improved by a factor of 2 with respect to what was done at Bell. Finally, in the flavor universality puzzles, we have the Bell2 first RD star measurement. It's not completely new, but has been published recently. And you can see that this measurement of RD star is bringing actually the Bell2 result to be compatible with the average, but of course it's not going to have a huge influence in the average of all the other results. And I wanted to mention 2 other results of lepton flavor universality, which are measurements that are now done on mass shells of the W, and these are done through the W produced in top decays, and you can see here a measurement done by Atlas, where you have a ratio of the muon to electrons, which is the best measurement done so far, and a very nice measurement, here I'm missing an equation, of CMS, of VCS through W decays from tops. I will add this for reference in the slides afterwards. And then finally, I also wanted to discuss briefly a measurement, two nice combination actually of measurements of gamma, which were presented this morning by Sneer, one from Bell2 and one from LHCb. So the Bell2 made a combination of the Bell results and the Bell2 results for gamma, which give an uncertainty and precision of about 7 degrees on gamma. And the latest LHCb combination that brings down the uncertainty to 2.8 degrees. So this is a beautiful result of LHC and Bell2. Also, Maurizio told us how nicely CMS is already doing analysis with parking data and scouting in its online chain, and showed first result with run-tree parking data, searching for the very rare D to mu plus mu minus decay, and had already very nice results with it. I also wanted to mention in the talk of David Rohr, who mentioned the next generation trigger project that is actually looking at larger scale projects to support the development of machine learning and large-scale models for high-energy physics. So this is a really very nice initiative that is going on currently at CERN. And then finally, I want to give us a brief focus on new states, and in particular, the observation of the Chi-C 3872 that was discovered about 20 years ago. But LHCb just recently has shown the measurement of 2 radiative decays of this state, and this is extremely interesting. So this is a tetraquark state, and these are extremely interesting, where you look at the decay of the Chi-C into the Psi2S and the photon, and the Chi-C to J-Psi and the photon. And when you look at this ratio, it's actually informing you on the actual structure of this tetraquark. And you can see that the measurement that's given here is a strong indication of a sizable charmonion or tetraquark compact component instead of a molecule of two D mesons together. And then also a very nice observation of a glue-like particle, and this is in radiative decays of J-Psi, which are very rich in gluons. So these are are good candidates to produce glue balls. And this, you have here this observation of this state at 2370, and it's a candidate for the elusive lightest pseudoscalar glue ball as predicted from latest QCD. And then in the charged lepton sector, we have a beautiful talk this morning by Toru Lijima, and also another talk in the bar session by Bogdan Malescu, and I'll try to summarize what the situation currently is. And first, I just wanted to mention a result from VEP with CMD3, which you can see here, the CMD3 measurement, which is coming from the direct scanning of E plus E minus data to pi plus pi minus. And this is now in complete agreement with the measurements from Fermilab. Well, the one intriguing thing is the change between CMD2 and CMD3, but this is currently being studied. But also, as Toru told us, there's this new BMW result that is using a lattice which is much finer and uses also long distance effect from E plus E minus data to revise the BMW estimate. And you see that now it's only at 0.9 sigma, so completely compatible with the measurement. Also, a very interesting aspect that was discussed by Bogdan in the parallel session is the fact that next to leading order radiative correction have to be taken into account when we try to measure the R ratio by radiative event, as is done in Barbara or done in Bell, but also done in Chloe, and this has very large impacts. So clearly, this type of effects have to be taken into account, and they will have an impact on the results. So we have to look up to this, but of course, the tension is decreasing. Okay, there was a beautiful result, and I want to highlight it, from CMS, looking at the tau anomalous magnetic moment through the photoproduction of taus in PP collisions. So this was already done in heavy ion collisions, but looking at vertices which are very isolated and with a low track multiplicity, you can actually measure the tau production in photon-photon fusion and be able to then assess the anomalous magnetic moment of the tau. And this is a beautiful measurement, and you see how much better this measurement is with respect to other measurements, like for Atlas from heavy ion collision data. And this measurement is only a factor of 3 above the Schwinger limit, the Schwinger term, which is the term of the anomalous magnetic moment coming only from QED. However, we should keep in mind that the Schwinger term is 3 orders of magnitude at least larger than any of the interesting correction to the anomalous magnetic moment. For example, if you look at the difference in the G-2 of the mu1 between the data and the prediction, the whole difference is the size of the electroweak correction, which is a huge difference. However, this is still 3 to 4 orders of magnitude below what is being measured with the tau, just to keep this in mind. Okay, then you move on to the neutrino sector, and I'll try to go as fast as possible because I see that I'm going to be running late. And we've seen from the two main oscillation experiments that are currently taking data and providing beautiful results in NOVA and NOVA from Fermilab B into Ash River and T2K in Japan. And you see that these experiments can measure both the disappearance of muon neutrinos and the appearance of electron neutrinos and antineutrinos. And you can see here a beautiful plot that was shown also by Pedro of the relation that you have between the measurements of these oscillations and all the parameters which are extremely important in the oscillation, delta CP, the mass difference, in particular the sin squared theta to 3, and also the mass ordering. So we see that we have a very interesting start of discrimination between the mass ordering. Of course, this is not going to be very significant in the end. There was a beautiful combination of the results from T2K and NOVA, which give a mild preference for the inverted order, very mild, but shows that CP conserving points are excluded at a 3 sigma level in the case of the inverted ordering, if I remember correctly. In the normal ordering, the CP valuation equals to 0 would be excluded about 90% confidence level. And of course, the final word will be given by the upcoming facilities, Dune and Hyperchemicande. One of the beautiful results that were shown at this conference is to see the emergence of atmospheric neutrinos using neutrino telescopes. And these are the results from ICECube with the deep core part of ICECube, and also KM3net with the ORCA detector. And you can see that in terms of sin squared theta 2.3, as well as delta m squared 3.2 or 3.1 in the case of ORCA here, you see that we have already competitive results with deep core that's going to be upgraded with 7 additional lines very soon, as well as ORCA that has only just a fraction of the lines that it's supposed to be having. And here I want to quote what Pedro was saying, is that actually atmospheric experiments are going to make a definitive measurement of the neutrino mass ordering by the end of the decade. So this is a very important aspect, is that if you look at the sensitivity that the experiments have currently, these are the experiments that are going to be probably leading the way to measuring the mass ordering in the very near future. And this will be also in conjunction with the beautiful Juno experiment, which is a 20 kiloton liquid scintillator detector that's going to be measuring the anti-neutrino disappearance from a reactor with a medium baseline. And this is an amazing measurement that should be able to look at this very tiny oscillation, in particular, a very specific interference pattern between that is going to be able to differentiate between the different mass orderings. And you can see here the sensitivity. So with Juno and the atmospheric neutrinos from neutrino telescope, we should be able to reach very nice sensitivities to the mass orderings very soon. Okay, and then Susanna showed us very beautiful measurements of neutrinoless double beta decay, and the leading one is the measurement from CAMLAND, which has the largest number of double beta nuclei, and you can see here that we're looking for a signal here in blue on top of, right in the middle of two very, very, very large backgrounds. This is extremely difficult measurement, but you see that the limit is already at the level of 28 to 122 milli-electron volt, and while the future is going to bring us to the level of 20 milli-electron volt. Legend 200 has also shown very nice results, not quite as good as CAMLAND, but they soon will be there, of course. And you can see here in summary where we're standing currently, which is at the level of 30 to 70, or about 100 milli-electron volt. So we are still way largely above the inverted hierarchy. But if we look at the next generation with CAMLAND Z1 and EXO, as well as Legend 1000, we should be able to fully exclude the inverted hierarchy. Susanna also showed us beautiful measurements, a beautiful update of the absolute neutrino mass limit using Catherine, okay, which is looking at this very high activity tritium source and just regular beta decay, and looking at the endpoint of the spectrum to actually measure the neutrino mass or put limits on the neutrino mass. And you see that the limit is now down to 450 milli-electron volt, and the final goal of Catherine is 0.3 electron volt. And you see here the limit with respect to where the inverter hierarchy would be to be able to be covered fully, and you see that this is going to still be quite far from it. Also, a beautiful emergence of the birth of neutrino physics at colliders, and you can see here the spectrum of neutrinos in various facilities as accelerators, but also in cosmic ray, high energy and ultra high energy cosmic rays. And you can see, for instance, that there's a hole in the middle, and this hole is actually going to be covered by collider neutrinos. And you see here both phaser and SND, two experiments that are put really down the beam axis from the collision point of Atlas, and they've been taking data up to now, and a very nice recent event. This is a data event from phaser that shows actually an event where emulsions that are being used in this experiment have been produced in Japan, taken to LHC, sent back to Japan, have been processed, and then now we have these beautiful events. And first measurement of electron-neutrino production at collider, as well as muon neutrino production at collider. Then we had a beautiful review by Katrin Zurek on dark matter searches and dark matter and possible dark setters. And she gave us this overview of the incredibly large, stunning range of possibilities for dark matter masses, ranging from 10 to the minus 23 electron volt to 1,000 solar masses. And she was kind enough to actually give us a very clear roadmap of what should be done, and in particular, starting from challenges, from a list of challenges. And challenge number 1, to fully cover electroweak Kino, dark matter, with Cherenkov telescopes, search for WIMPs to the neutrino background in direct detection, build out the suite of accent searches to cover very low masses of dark matter, build out the suite of accelerated searches, a high energy and intensity for hidden sectors, cover the abundance-driven light dark matter models in direct detection, observe the dark matter powers on small scales. So I'm going to follow these very nice guidelines, and as you will see, Jocelyn and Stefania have covered actually most of them. But to start with, I just want to mention what Catherine told us about. The first challenge is to fully cover the electroweak dark matter. If you look at the limits, I will come back to this later, of the searches for electroweak, so SUSY particles, SUSY like neutralinos at LHC. LHC is not particularly well suited to find high-mass electroweak. However, Cherenkov telescopes are, and this is extremely interesting, to cover the full mass range of larger masses from, say, about 1 TeV or slightly below 1 TeV up to hundreds of TeV mass scale. And another challenge is to observe dark matter on power scales, on the small scale subhalos. And she showed this very nice matter power spectrum from Planck that shows what are the main scales of structures that are observed. And it's very interesting to look at very small structures because they can teach us about models of dark matter that are extremely massive, like primordial black holes, or even models where we have accent dark matter. And the challenge number 2 that was mostly discussed by Jocelyn is search for WIMPs to the neutrino background in direct detection. And this, of course, is a very important aspect. And just to summarize where the searches are, you see that the currently excluded limit are here. You see here the neutrino floor, or the neutrino fog. And you see, for example, here in this region, where we're close to the boronate solar neutrino type of events. And you see that we're getting very close to the neutrino fog. And you see also, so here we have a large number of operating detectors, Xenon N-ton, Panda X 4-ton, Lux Zeppelin 7-ton, and DarkSide, which is coming up. And next generation with Panda X 20-ton and Darwin X LZD, as well as DarkSide 20-ton as well, that I haven't mentioned here. I will add it to the list. And then you see that the limits should be able to go down to much lower. So with the operating detectors, we should go here down to this green curve, so within the reach of the neutrino fog, and in the plant detectors will be completely in the neutrino fog. So this is what was required by the challenge of Catherine. And here I just wanted to show you a beautiful result obtained by Xenon with the data of 2 years of the SR0 and the SR1. And Xenon is taking 2 types of signals from the liquid xenon scintillation as well as the ionization silent where electrons are drifting and are ionizing and then depositing a signal in the gaseous xenon scintillation. And here we have 2 types of events, electron recoils. And already in the electron recoil, there's an extremely interesting physics. In particular, there's the observation of the double electron capture decay that you can see here in the peak right here, but also in the very small peak here, which is less sensitive, of course. And also, it's going to be possibly sensitive at a certain point to solar neutrinos from the PP and beryllium-7. However, this is still very, very subdominant. Now, the very interesting aspect that was shown by Xenon at this conference was the observation of nuclear recoils coming from boron-8 coherent scattering of solar neutrinos. And this is very important because it shows that we are now reaching the neutrino fog. Can I have just a couple of minutes more? Okay, so then important third challenge that was discussed by Catherine is to build out the suite of accent searches. And Jocelyn showed us that either by light shining through a wall, by helioscope with sun shining through a wall, or in haloscopes with dark matter shining through a wall, and you have a suite of very nice projects that are going to be covering a lot of the parameter space, but there's still a lot to be done. And then the challenge number 4 is to build out a suite of accelerated searches for high energy phenomena and in the intensity frontier. And this was discussed mostly by Stefania to look in the TEF scale, but with small couplings where we're going to be looking at long-lived particles in the detector, or in high intensity facilities looking at sub-GeV new physics that's motivated by decays of meson, for example. And here you have many facilities that are foreseen also for this type of searches. And then finally, also Catherine told us in her 5th challenge that looking at covering the abundance-driven light-dark matter searches, actually just 1 kilogram ear type of detectors can give you immediately excellent reach and sensitivity. And here there was a beautiful talk that was given by Michael Dozer, explaining really how much progress can be done with quantum sensors to be sensitive at very small energy recoils. And then there was this beautiful event. So this is the ARCA detector from the KM3Net collaboration. And this is an absolutely beautiful event of one single muon that is in the range of 100 TeV. So this PeV, sorry. Beta electron volt. This hasn't been published yet, so this is very preliminary. But Pascal, the spokesperson of the collaboration, was kind enough to give me this beautiful animation. And you can see these fantastic neutrinos. So these type of neutrinos have to be, so these can only be produced from a neutrino and can only be seen when the neutrino is really very horizontally interacting very close to this to the detector. Now, 100 PeV neutrino means muon means that the initial neutrino would be of the order of 3 times that, more or less. Okay, and the highest energy neutrino, mu neutrino, which is the highest energy neutrino that was observed in the IceCube so far, was at the level of 10, 12 PeV. Then Vitor showed us beautiful results, in particular, with twice the data set that has been shown so far, the measurement of positrons in IMS. And we all remember that many years ago, the first measurements that were slightly discrepant from the positron from cosmic rays, that was showing that there was a deviation. And this could be due either from dark matter from annihilation or from new sources like pulsars. And this is very interesting, in particular because we see a cutoff on the spectrum. This cutoff on the spectrum indicates what type of mass of dark matter this actually could be. So these are very high dark matter candidates. There's also a beautiful result shown by LHCb in the production of anti-helium-3. And anti-helium-3 is an interesting measurement from LHCb because AMS is looking for anti-helium-3 as a sign of dark matter annihilation, which has which likes to actually annihilate through a lambda b at certain given mass ranges, and then decay to an anti-helium-3. And this is very interesting to be measured in PP collision, and this was done by LHCb. Now, the beautiful event in multi-messenger astronomy that was shown both by Samia and Vitor is, of course, the conjunction, the detection of gamma ray bursts from Fermi as well as integral in conjunction with the gravitational wave, both in the LIGO Hanford and LIGO Livingstone. And you see here the beautiful signal observed with the chirp here in LIGO, as well as the observation both in integral and in Fermi of the gamma rays. And this is very interesting because it allowed them to put actually limits on test of the speed of gravity and equilibrium principle, as well as constraining models of the neutron star equation of state. And this leads me actually to even denser nuclear matter with heavy ions. And you have another beautiful result from Alice that has shown the production of anti-helium-3 in lead-lead collisions. And you can see that this can be measured with a beautiful particle identification in Alice. And this is a very nice probe of collective expansion microscopic models. I also want to take this opportunity to highlight one of the very nice upgrades that are foreseen by Alice for the long shutdown 3. That is the ITS-3 upgrade of the innermost layer, pixel layer of the detector that's going to be using this monolithic CMOS detector, so monolithic active pixel sensor maps. And this is beautiful because it's really bent sensors that have the ASIC directly built in. And these are incredible, since the first detection layer is going to be brought to an unprecedented medium of 0.05% x0, and it's going to be at a distance of 18 millimeters from the beam. And then Magdalena showed us a very beautiful framework, DRINA, that allows you to make a Bayesian analysis of high transverse momentum as well as low transverse momentum observables of the QGP, and able to give fantastic, able to give nice constraint on fundamental parameters of the QGP. Felipe gave us also very nice results with the first year campaign of DAISY, which is dark energy spectroscopic instrument that is surveying and making a three-dimensional mapping of galaxies. And you see a beautiful picture of this DAISY 3D map. And from the analysis of these maps, one can infer the baryon acoustic oscillations, so this characteristic co-moving separation, so this scale in distance that is characteristic of the expansion of the universe given primordial fluctuations of the early universe. This analysis has been done with 6 million spectrum grouped in 7 different redshifts, and you see here the splitting. So it was hard for me to actually understand each of these labels, so it was fantastic that DAISY produced a cartoon that I was able to understand on what all these measurements correspond to, so you can see them here. And from these data, DAISY was able to actually produce a new measurement of the Hubble constant that has not released the tension, which is one of the large tension and puzzles so far, and a beautiful measurement of the limit on the sum of the mass of the neutrinos from the cosmology, which of course is relying on cosmological assumption. But you see that the limit which is obtained by DAISY and the CMB, so the Planck data, is already at the level of 72 milli-electron volt, which means that actually, if you take at face value, this limit is essentially already in tension with the inverted hierarchy. Okay, I will finish with direct searches. I'll go fast. It's important. Livia showed us a suite of beautiful new searches from Atlas and CMS. And one, which is a run-3 search on improving reconstruction techniques in Atlas with large radius tracking. This is very interesting, but I will skip it. And searches for electroweak production in compressed scenarios. This leads me to a bigger picture of where we stand in searches. In particular, I wanted to highlight the stop searches, and you have this comprehensive review of all the stop searches that have been done so far. And I wanted to point out that if you look at the limits, this is again to discuss what are the limits that are set so far by LHC, we're at the level of slightly more than 1 TeV for stops. And slightly more than 1 TeV for stops means that the tuning in terms of the mass of the Higgs boson is a factor of about 20. So the tension is already strong. However, it is not strong enough to actually completely rule out naturalness. And we can look at also our Gluino searches, and Gluino searches are at the level of 2.5 TeV. And also Gluino, it's also in the case of Gluinos, stop are also scalars, and it requires light Gluinos to be light enough. And also our intention, in this case, the tuning factor, when we take Gluinos, and the limits on Gluinos are 3 TeV, the tuning factor is about a factor of 30. And in summary, you can see that, so it's always very instructive. You can look at these plots. I mean, of course, these are a huge number of searches. However, it's useful to see what is the current typical limit on new phenomena that we have at the LHC, and the limits are typically at 2 TeV in the case of SUSY searches. And when we expand it at the HLHC, we see that these limits are going to go to about 3 TeV. And what this means is that there's still a large domain of possible discoveries and in terms of gluinos, up to 2 to 3 TeV, in terms of stops, up to 1.5 TeV, and electroweak SUSY up to 1 TeV. Same for high mass resonances, and you see here, for instance, the limits are higher currently at about 4 TeV, and the reach is going to be going all the way to 8 TeV. So the discovery potential goes up to between 6 and 8 TeV at HLHC, and for leptoquartz, for example, between 1.5 and 2 TeV. So what's interesting also is this beautiful event that was mentioned also by Livia, an 8 TeV CMS dijet, so 4-jet production, where 2 jets are actually have a mass of 1.8 TeV. So this is, of course, extremely interesting, non-significant for the moment, but potentially interesting for the future. And then finally, I will finish with prospects for the future that were discussed by Rende, and I will try to split things in a very simple way. So I see that simulation is not perfect yet. So first of all, most importantly, we have to finish the full LHC program, which is going to run up to 2040. And then we want to have an ultimate precision E plus E minus machine, and finally an ultimate energy 10 TeV center of mass, parton center of mass and energy machine. And Rende explained to us that there are projects that can start before 2040, and these are CLIC ILC, Cool Copper Collider, and CEPC, and projects that will start normally fairly soon after, hopefully, like FCC and the FCC in the longer term. So, as the rector of the university told us at the very start of the conference, the field is really facing a defining moment in its history. And I think that Hitoshi has put it in a perfect way, where we're actually standing in the question of what should the future large collider project be. And in very simple terms, Hitoshi told us that it should reveal the secret of the Higgs boson. So this is one of the conclusions of the P5. I would add also that, and much more, because we really want also the ultimate electroweak precision factory. In particular, we would not be, and here I'm quoting Gavin Salam and collaborators in this very nice Nature paper about the Higgs anniversary. We could not consider the theory of electromagnetism to be fully established if we had verified it just at a few % level. And this is, of course, true, so we need precision. But also, we need a realistic path toward a 10 TeV parton center of mass energy collider. And this is also extremely important. And on this, I will close with closing quotes from DGs at the panel yesterday. First, from Yifang Wang, who said, in the future, not very far from now, there will be a Higgs factory. From Leah Merminga, sorry, this was automatically corrected, we need to continue to be bold and ambitious and dream big. And finally, Fabiola told us yesterday that, as we have seen at this conference, the field is extremely vibrant and exciting. I hope that I've illustrated this in this talk. And I thank you all. I thank, in particular, the organizers, and congratulations to all the speakers and all the participants for the very interesting discussions. Thank you.
Thank you very much. I failed to cut you, but I don't regret. I hope you don't regret either. Still, I think time for 1 or 2 questions. So is anyone who want to comment, who want to ask something? Again, it's very difficult for me to recognize some hands raised. Looks like not. So you were really very clear. Or people are on rush for their plane or something. So I think let's thank the speaker again. It was really deserved. And next, we will listen some invitation to the coming large conferences where these discussions will be going on. So first, our colleagues from EPS-HEP.
Yes. So thank you very much to Zdenek and Tomas for accepting to reserve these few minutes to present the next large conference of the field, which is EPS-HEP 2025. I am Cristinel Diaconu, and I'm from Marseille, CPPM, and I'm chairing this conference with Thomas Strebler, so the number of Thomas will be conserved for the next conference. The conference is one of the EPS, European Physical Society series, started in the 70s, and is driven by the EPS-HEP board. It's a conference which has a similar structure with plenary sessions, about 12 tracks in parallel sessions. However, the schedule is a bit different. It's from Monday to Friday, so you have 2 weekends around, but the conference is running in a row. The plenary sessions are around lunch, so it gives a different kind of setup. I didn't prepare slides because I thought by now you had enough. So I did prepare a movie, and I will also comment on this movie. So if you can start it. So this is Marseille with the emblematic Notre Dame. That's the old harbor stadium. So that's around the conference place with a few emblematic places. Museum. And this is the conference place. That's the palace where we are going to have the parallel sessions. It's just near the city center. There are accesses from main capitals and so on. It's not far from CERN for 4 hours of train. That's one of the touristic spots. The sea is nearby. So that's the conference place, right? And of course, many results will be expected. We'll have also a pit stop of the European strategy with the workshop taking place 2 weeks before that conference. There will be an EPS session during conference. So thank you very much, and we welcome you in Marseille in 2025.
Thank you. We are looking forward. So thank you for the presentation. And next presenter is Rogerio Rosenfeld, who will present the invitation to the next ICHEP.
Okay. So I'm absolutely thrilled to announce to you the next ICHEP in 2026, which is going to take place in Natal, Brazil, from July 29 through August 5th. And I have to confess, I'm a little bit scared also of the responsibility, especially after this flawless organization of ICHEP here in Prague. I want to say a few words about why ICHEP in Brazil, why this is important. This is historical, in my opinion. It's the first time that ICHEP will be hosted in Latin America. And Latin America, I want to show you later, that has a thriving high-energy physics community, which was mapped by the Latin American Strategy Forum for Research Infrastructures, which we call LASFRI, in these areas of HEP. And recently, we have formed a Latin American Association for HEP, and also, and this helped in the community organization of these areas in Latin America. As you are probably aware, Brazil became an associate member of CERN this year as the first country in the Americas. And the Brazilian Physical Society, which is helping us in this organization, has experience in organizing events for more than 1,000 participants. We have the support from the Science and Technology Ministry and several agencies and institutes in Brazil. Natal, the city where the conference is going to be held, is a beautiful city by the ocean with excellent tourism infrastructure and good flight connections. And also in Natal, there's the International Institute of Physics, which is also going to provide infrastructure for us. Also, we envisage the possibility to organize satellite meetings in other countries or places in South America, in Latin America. So I want to show you that there is a rich and diversified landscape of Latin American participation in international collaborations in high-energy cosmology and astroparticle physics. And this was mapped a few years ago by the Latin American Strategy Forum for Research Infrastructures in ICHEP, and you can find all the documents here. And we are now in the process of updating this landscape, but I will show you what we had so far. It's a very busy slide, but I want to show you that the countries that we have mapped so far in Latin America are involved in several international collaborations. These are the astroparticle cosmology collaborations. These are the high energy or nuclear physics collaborations. And these are the neutrinos and dark matter collaborations. So you can see that there is a very complex landscape that we mapped. And there's a large community that is involved in several of the experiments and in the areas that this meeting wants to cover. So the venue for ICHEP, we're planning to have two venues, actually, one for the parallel sessions and the other for the plenary sessions. The venue for the parallel sessions is going to be this Praia Mar Natal Hotel and Convention Center, which is located along the beach here. And the venue for the plenary sessions is the Natal Convention Center, which was recently renovated, and so we plan to use this center. So this is the map of Natal, and here is the Praia Mar Convention Center for the parallel sessions. This is the Natal Convention Center. The distance here is about 1.5 kilometers, so it's 20 minutes walk. This is the ocean. There are several hotels around and restaurants, so it has a very good touristic infrastructure. This is the International Institute of Physics, which is located in Natal, and they are giving us full support, and we can also use this to propose activities for the event, or satellite meetings as well. So Natal is in a very nice area in Brazil with dunes and oceans and art crafts. All of this you can probably have a chance to see. This is, for those of you that don't know, this is a cashew fruit. And this is the cashew nut that you eat sometimes. And it's one nut per fruit. And they claim that they have the largest cashew fruit tree in the world. You also may be worried that it's winter time, as you probably know, in the southern hemisphere. But don't worry, this is the weather forecast that I got a couple days ago. So the weather is pretty much like here in the winter. So so Natal is, so this is, I just want to show you geographically where Natal is. So this is Brazil. It's a very large country. And just to give an idea, Rio de Janeiro is here, São Paulo is here, the Amazon forest is around here, and Natal is in the northeast of the country, and geographically is closer to Africa, Europe, and the United States. And it has directed flights from Buenos Aires, for instance, and also from Lisbon. And there are flights that serve cities that are around Natal. For visas, you can always get the official information in this link, but at the moment, citizens from the US and from most countries in Latin America and Europe have visa exemptions for a period of not exceeding 30 days, but you should check this link periodically. We already set a local organizing committee. Probably you have to put more names here. After talking to the organizers, we realized that we need more people to work. Ignacio Bediaga is the co-chair. He's here, as well as some of the members of the local organizing committee are present in the ICHEP. Vitor de Souza gave a very nice plenary talk on astroparticle physics and multi-messengers. And I hope to see you in Natal in 2026. Thank you.
Thank you very much. And we are definitely looking forward, yes. And so
it's going to be a tough job.
may I ask the speaker of the last talk, of the closing remarks, my colleague Tomas Davidek.
Okay, so good afternoon, ladies and gentlemen. So it's my great pleasure to present the final closing remarks. Okay, so first of all, I would like to thank the sponsors, and the co-organizers from the other institutes, whose logos you can see on the side. So especially to UPAP, who provide some sponsorship, and then the co-organizing institutes. Okay, so here are the logos of the sponsors. We were happy to have them so many. And but of course, the most important content of the conference is due to excellent talks and posters that we have seen over the last week. So just some statistics: there were 918 talks and parallel sessions, 45 excellent plenary talks, and we were going through almost 300 posters. So we were very lucky to get so many of you here. So there were almost 1,400 participants here, plus, as we announced earlier, the plenary sessions were streamed to YouTube. So there were up to 900 people watching YouTube, and in total, and the live peaked at 140 watchers on YouTube. So that's also nice. Okay, so as you saw, that we have gathered quite some photos during the conference. So those who are interested later on, so you can pick them up in the Indigo as shown on the side, and also some more pictures can be found on Instagram. So I would like to say huge thanks to all the participants, as I hope that most of you can find yourself in the conference photo here. And also we are grateful to the International Advisory Committee, it is listed in the top of the slide. And I would like to also express big thanks to all the parallel session conveners. There were almost 80, the non-local ones. Also, we got a lot of help from the volunteers wearing the violet T-shirts. So they helped us not only with bringing the microphones, but with many other things. And unfortunately, not all of them are in the photo, so but okay. And last but not least, the local organizing committee. So here at so this is the list of people, and soon we will bring to the stage the leaders of the individual working groups. So so before we get to that, so I would like to wish you a safe trip back home, and as Rogerio, previous speaker, already said, see you all in Natal at ICHEP 2026. So thank you for your attention, and thanks for coming to the conference. And now I would like to call to the stage the working group leaders of the local organizing committee. Please come. We are still missing Anna from the scene agency. Oh, she's coming. Perfect. Jo, dáme kříž. Jsem tě teď nefotil.
So also from me, thank you very much and have a safe trip home.